Alright, we're going to be looking at bipartite graphs, lesson 6 for this video. Okay, so what we want to be able to do is bipartite. We obviously need to understand what this is in terms of a definition, construct the graphs associated with this as well. Here we go. Alright, if we have these vertices like so, we have the people across the top and we have the places across the bottom. What we want to be able to do for this one is the edges that connect the students to the capital cities that they have in fact visited. So as an example, Asher has visited Paris, Sydney, Macy has visited Paris, Sydney, London, Karis has visited London and Tokyo, etc., etc. Okay, so we can see the places which these people have in fact visited. Now what we notice is that we have two distinct groups. So within these two distinct groups is obviously we've got the people across the top, and we've got the places across the bottom. The thing you notice with bipartite graphs is that it separates them into two, which means that within the top group up here, so within the top group, what we notice is that no one is connected to each other through an edge, and within the bottom group effectively is that we have no one is connected to each other within the bottom group. All right. So what we mean by that is that as soon as I create or add an edge in, which might in fact be from Paris to New York, the graph would no longer be bipartite. Okay, so bipartite means that you have two distinct and separate groups which are not connected by any edges. Okay, and that's what we're just summarizing here. There are not any edges connecting students to students or cities to cities. All right, so we said this is called a bipartite graphs. Okay, we need to be able to create the graph, and we'll have a look at a little question as to whether these graphs are bipartite or not. First one, nice and easy, is that we can see we have two distinct groups. We've got 1 and 2. That's nice and simple. Within those two groups, no one is connected to each other, which makes it very simple. All right. Color coding is quite a good way to do this. All right. So when you're color coding, all right, is it works really easily for the first one. Second one, again, works really easily. The third one, this is more a test level question, is what you would say, something along these lines. All right. So what we mean by that is that they may in fact give you a graph like this. All right. And what we'll be able to do with this third one is we need to be able to try and construct this. All right. And okay, we've just said that. Is we need to be able to try and construct this into a bipartite graph. All right. Or prove that it is in fact a bipartite graph. So what you need to be able to do is redraw this effectively. Okay, so we're going to run over how to do that. Let's go back and let's figure out how to do that. All right, so there's a few options of how to do this. Number one, the color option is in fact quite good. So we've obviously got the dark circles and the light circles. So within the dark circles, okay, start with any point that you want. So for example, this one, okay. Now, anything which is connected to this red dot must mean that it is in fact in the opposite circle. All right, so if I call this letter A or point A, right, I'm going to label it down here. It's going to reappear in a moment. If that is point A, what I would then have is I'm going to call this point B, C, and D, means that B, open circle, C, and D must be opposite. Now, as I'm starting to construct this, what I want to try and do is also put in the edges as well, right? 1, 2, and 3, those 3 lines that I've drawn. Then I go to my next one, okay? I'm going to go to this one here, which is going to be E, and this one here, which is going to be F. Now, they are both connected to the light circles, which means, right, that they must be opposite, so they must be in the top, as they were previously colored before. So we have E and we have F. So E is connected to D, so make that connection there, highlight it as I go. C is connected to E, so once again draw it and highlight it as I go. And C is connected to F, draw it, highlight it as I go. And lastly, B is connected to F, like so. Alright, so as I go, I highlight each of them. Continuing on, okay, I'm going to continue to label this one. I'm going to call this one here G. Alright, once again, it is connected to E and F, which means it must be opposite E and F. So it must be down the bottom here, like so. they're my two lines I've drawn, so it must be connected to E and F, like so. All right. Try and keep it nice and neat. And last point, H, and H is connected to D and B, so that means H must be in the top group. So H is connected to D, and H is connected to B all the way across. I've missed one, H is connected to G as well. All right, so as I'm going, I'm highlighting each of the lines to ensure I don't miss any. Now what I can see is I can in fact see that it is in fact bipartite. All right, so that's one way to do it, okay, to actually reconstruct and redraw it as a bipartite, okay. The other way to do it is to simply ensure that when you are doing the colored dots on each of the vertices, is all you need to do is actually just check to see that there is no same colored dot touching each other. All right, so what we mean by that is if I look at point G there, every edge which it's connected to is a dark colored dot. When I look at point H, every dot connected to H is a light colored dot, etc. Okay, go to C, every dot connected to C is a dark colored dot. If I had another light colored dot connected to C, as an example, if C was connected to D, that would mean it would be no longer bipartite. All right, and we'd see that as a line going down the bottom like so. Okay, all right, and there's my drawing down the bottom. Okay, so you will in fact be asked within a test to reconstruct these. Okay, so you need to be able to do that. All right, some more definitions. Complete, you should know what complete means in this point. So complete means every vertex in the first group is connected to every vertex in the second group. All right, like so. So there's 4 vertices in the top, which is connected to each one of the 3 vertices in the bottom. The way that we can calculate that is we can do m times n. M is the number of vertices, so for this example here, okay, we have 1, 2, 3, 4 multiplied by 3. So for this example, answer there is going to be 12. All right, so for this diagram here is we have 12 edges connecting them all. All right. Here's another example of that test, okay, to see whether it is in fact bipartite or not, okay. Use 2 colors as we just suggested. We'll go through this a little bit quicker. So what we firstly said is color any of the dots in one of your colors. For example, B has been colored in red, all right, and that means that anything touching the letter B via an edge must be colored in blue, like so. So we've got A, C, and D colored in blue. As we then go across, anything touching those blue ones must be the color red, which is going to be E and G. And then double check to make sure that there is in fact no connection from B to E, because if that was a connection there, it would no longer be bipartite, as we said before. Then what we would have is we would have F would in fact be blue, because that's attached to G and E. Now, here's where it makes it nice and simple. What you then do, take all your blue dots, all right, and watch this, and they form one group like so, A, C, D, okay? Take all your red dots, and F, sorry, and take all your red dots, B, E, and G, labeling each of them, obviously in the diagram, and then making all the making all the connections that you have. All right, double check that the number of edges that you've got in the diagram, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I counted that correctly. Right, obviously matches up with how many you've got here. 1, 2, 3, 4, 5, 6, 7, 8, and the one going across there, 9. All right, can get a bit tricky with obviously the edges which cross over. All right, that is it.